6-7, we're going to look at performing similarity transformations. Now, we haven't talked a ton about transformations in general, but what transformations are is they are taking a figure and doing something with it, whether it means moving it up, moving it down, left, right, enlarging it, rotating it. There are numerous types of transformations that we're going to discuss, but in particular in this section, we're going to look at a similarity transformation called dilations. Now, when you think about your eyes being dilated, most of us have had that happen. What happens is when your eyes are dilated, your pupils get extremely large. Okay, and so some vocabulary. What a dilation is it's a transformation that stretches or shrinks a figure to create a similar figure. Okay, so the only type of transformation that we're going to talk about that is a similarity transformation is a dilation. Why? It's a transformation, and whenever you perform a dilation on a figure, you create a similar figure. Okay, so your original and your new one are similar to each other. In a dilation, a figure is enlarged or reduced with respect to a fixed point called the center of dilation. Okay, and we're going to use the origin as far as we're concerned. Okay. So the scale factor of a dilation, we use the variable k, the letter k, to represent scale factor, is the ratio of a side length of the image to the corresponding side length of the original figure. Okay, you could set up the ratio of x or y coordinates; it won't matter. Okay, the big thing here, it's always new over old. Okay, new over old. Okay, so it's the image over the original. So the new one here, as far as we're concerned, the A prime is the new one. Pick either or. I'm going to use x coordinates. So the new x coordinate is 10. The original x coordinate was 5. So my scale factor is just 2 to 1. Okay. And so scale factor, new over old. The coordinate notation for a dilation, very simply, is using coordinates. Okay, you can describe a dilation with respect to the origin with the notation xy goes to kx comma ky, where k is a scale factor. Okay, k is a scale factor. So it looks something like this. Okay, that's all we're doing there. A dilation where k is between 0 and 1 is a reduction. Okay, so if xy is given to you and your dilation is 1/2 x times 1/2 y, well then that's clearly going to be a reduction. You're getting smaller. And if k is larger than 1, it's an enlargement. Okay, so if this is 6x and 6y, well clearly you're getting bigger. So example 1 says find the coordinates of L, M, and N so that triangle LMN is a dilation of triangle PQR with a scale factor of K, sketch PQR, and LMN. So my scale factor is 2. So then that means that the coordinates of L are -4, 6. Coordinates of M are 4, 2. And the coordinates of N are -4, -4. Again, all I did here was I took these two, multiplied them each by 2. Multiply these guys by 2, and multiply these guys by 2, and that's where I get my new coordinates from. All right, and so when I graph them, okay, I'm just going to sketch them really quick. So here's my xy. P is -2, 3. So there's P. Q is 2, 1. There's Q, and R is -2, -2. So there's R. So here's my initial triangle, the red one. Okay, now I'll plot the new one in blue. So I have -4, 6. So we're up here. So this is L. M is 4, 2. And N is -4, -4. And so the blue one would be my enlarged figure. So in other words, the blue one is exactly 2 times larger than the red one. Okay, it says draw a dilation of quadrilateral ABC with vertices. The scale factor is 1/2, so you know it's a reduction. Okay, so my new coordinates, A prime is going to be 1/2 of 2 is 1, 1/2 of 0 is just 0, 1/2 of 6 is 3, 1/2 of -4 is -2, 1/2 of 8 is 4, 1/2 of 2 is 1. And finally, 1/2 of 6 is 3, 1/2 of 4 is 2, Okay, so all I have to do is plot my new point, my new coordinates. Okay, so I have A prime 1 0, B prime 3 negative 2, C prime is let's call this A prime, B prime, C prime is 4 1, 2 4 1, and D prime is 3 comma 2. And so there's my figure. Whoops, wrong spot. So there's your dilation. A triangle has the vertices 2, negative 1, 4, negative 1, and 4, comma 2. The image after dilation with a scale factor of 2 is DEF. Sketch them both. Okay, sketch them both. So I could sketch my original. I'm going to sketch it in blue here. So I have 2, negative 1. 2, negative 1. There's A. B is 4, negative 1. 1, 2, 3, 4, negative 1. And C is 4, 2. So here's my original. And my new one now, okay, again, scale factor is 2, so D is going to be the point 4, negative 2. E is the point 8, comma, negative 2, and F is the point 8, comma, 4. All right, so I plot those points. 4, negative 2, 1, 2, 3, 4, negative 2. That's going to be D. Point E is 8, negative 2. So 4, 5, 6, 7, 8, negative 2. And F is the point 8, 4. 1, 2, 3, 4. And so here is my new triangle. It's exactly twice the size with respect to the origin. And that's kind of what you're looking at. And really, where this comes from is the idea that if this is the center of my dilation, the origin, then I can draw a segment going through point A and point D. Okay, and then if I draw a segment going through C, it's also going to go through F. And if I go through B, it's also going to run right into E. That's kind of where this idea of the center of dilation comes from. Okay, part B says verify that they are similar. Okay, and so when I do this, I can do this a few different ways. You know, what I'll do is I'm just going to go ahead and look at the length of each side. So I know I'm going to use our side angle side shortcut here, because if I look at the length of AB, that's easy to find, and that corresponds with the length of DE. And I can just count here. The length of AB, if I look back up at my graph, is 2 over the length of DE is 4. That's 1 over 2. And then if I also look at the length of BC over the length of EF, I can count again. The length of BC is 1, 2, 3. And the length of EF is 1, 2, 3, 4, 5, 6. And that's 1/2. Check, check. Those are the same. And now if I look at these angles here, angle B and angle E, I can show that those are actually congruent angles. Because here's what I know. I know that the slope of AB is 0. And I know that the slope of BC is undefined. And so what that tells me is that AB is perpendicular to BC. Therefore, angle B is 90 degrees. Okay? And I can also use the same argument in the bigger triangle, right? The slope of DE is 0. It's a horizontal line. And the slope of EF is undefined. It's vertical. Okay? Therefore, DE is perpendicular to EF, which means that the measure of angle E is 90 degrees as well. And so since that's 90 and that's 90, these two triangles have to be similar because of SAS. Example 4 says Josie is making photo magnets. Her original photo is 8 inches by 10 inches. The image on the magnet is 2.8 inches by 3.5. What is the scale factor of the reduction? New over old. K equals scale factor equals the new. I'm going to compare 2.8 and 8. Okay, and it doesn't matter. You could have done 3.5 and 10. You're going to get the same answer. Okay, so I have 2.8 over 8. Okay, and you can leave it like that, or we can just go ahead and get us a decimal. So if I do 2.8 divided by 8, I get 0.35 would be my scale factor. If you want to write that as a fraction, you can do that too. It's not going to make a bit of difference. Okay. Okay, example 5a says Mrs. Shooks wants to create a quadrilateral JKLM that is similar to quadrilateral PQRS. What are the coordinates of M? Hint, first find the scale factor between the image and the original point. Okay, so here's what I do know. Okay, I know that my figure, okay, let me trace the original. It's kind of hard to see what's going on here. The original is PQRS, so PQRS. So there's my original figure. My new figure is JKLM, so JKL. And now the question is, where does M have to go so that we are similar? Okay. Now, if I look at this, what I do know is I know that based on the names, JK and PQ correspond. I could use length there, or what I can do is I know that point J corresponds with point P. And I can see pretty clearly here that point P is a point 0, 1, 2, 3. So this is 0, 3. And point J is 1, 2, 3, 4, 5, 6. Is 0, 6. And so when I compare the y coordinates of these two, 6 and 3, that tells me to go from my original, right? It's new over old. So my scale factor, they already have a spot here. Scale factor, my new y coordinate 6. My old one was 3. My scale factor is just 2. So now in order to find the coordinates of M, I know M corresponds with S. S is the point 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So I know that M, just double those. Multiply those by 2. It's got to be the point 10, 10. Let's see here. 5, 6, 7, 8, 9, 10 out here. And then up 10. 5, 6, 7, 8, 9, 10. It's going to be up here. So point M is the point 10, 10. And there's your enlarged figure. So a little bit different, applying this idea of a scale factor. I'm going to let you guys go ahead and work through part B as the same type of problem. Okay. So again, you've seen how we can ask you just to perform a dilation. We can give you a dilation and ask you to find the coordinates of a specific point using scale factor, etc., etc. So I think dilation is pretty straightforward and usually is one of the easier transformations for students to handle. So hopefully you feel pretty comfortable with it. If not, as always, bring questions to class and we'll work on resolving those in class.